I would like to thank the organizers to have me here, but I guess you're part of the organizers as a representative, Graham. Yeah, this is the Jenny and I have a sequence of talks, Jenny Wilson and I, and this is the first one. We're going to have 3 talks about math, and then we're going to have 2 exercise classes where we just give you exercises and you can ask questions. And then the last lecture is going to be an extra lecture on what else is there, further directions, what other theorems are there, and also what are open questions, especially are there anything that's approachable as a grad student, and I assure you they are. And yeah, let me, and so this first lecture is going to be, I'm not going to say too many new things other than what among all the different talks that have already been this week and last week. But I'll have a little bit of a more hands-on approach. I'm going to tell you a little bit more concretely what things are in very specific cases. So feel free to ask any questions. And as I said, I'm just going to stop whenever I need to stop, and we'll have covered something. It's just like sort of getting into the groove of what we're doing. Maybe one more thing. So the lectures that we're giving is much less computational. We won't have any algorithms or anything. It's very theoretical in nature. But so the main point is for you to understand some of the theory. So yeah, let me start with that. Let me just start out with, I mean, this is perfectly redundant, but maybe it's always good to start out with something that's completely known, and then you can move on from there. And so I'll talk about SLNZ, and as we've talked about different things already multiple times here, this is the n by n integer matrices with determinant 1. And then the other main player that I'm going to talk about is principal and mostly prime level congruent subgroups. So my notation for that is going to be gamma NP, because I'm looking at it in, I want to make sure that I know in which SLN I'm sitting. Then P is usually a prime, but it doesn't, yeah, I guess for my notation, what I'm going to write is going to be a prime. But this is literally all of those matrices such that in SLNZ, such that A is congruent to the identity matrix mod P. And another way of framing this is the kernel of the reduction map from SLNZ to SLN FP, or I guess if P is not a prime, Z mod P. So this is the reduction map mod P. So these are two groups that we're going to consider, and let's see what we want to, what do we want to do with these groups? Well, we want to investigate the high cohomology of these groups. Let's say with here, maybe with Q coefficients, with trivial coefficients, and here for these congruent subgroups, we can probably even say something integrally because they're torsion free. And this is, so this we want to do for large I, and we shall see later that large I, and we've maybe already seen this before, that large I here means that it's below or like close to closely below n choose 2 in this case, because, and that we will see that later, that hi of these groups, let's see, with these groups with q coefficients is 0 if I is bigger than n choose 2. That we will see in a little bit. Okay, so that's setting us up. So this is what we want to talk about. I will talk a little bit about how we find this and how we access these groups for large I today. Then Jenny will give 3 talks, and she will focus on I being equal to n choose 2 for SL and Z. And there's going to be a lot of different things coming in, especially simplicial complexes that we will have to show that are highly connected is something that comes in there concretely. I will then give a lecture about n choose 2 minus 1. So that's like the codimension 1 case for SL and Z. And in my final lecture, I will give I will consider gamma NP in codimension 0. That means for I equals n choose 2. That's kind of what we're set out to do. Okay, so let us first start by recalling symmetric spaces. And I can imagine that all of you maybe know even more about this stuff than I do, but I'm looking at this quite elementary. So I'm just going to define a space Xn to be SLNR mod SON. So real determinant 1 n by n matrices mod the special orthogonal group n by n matrices. Now this is not a group. This is not normal in there. So this is a space. There is a zoom issue. Oh no! Oh, this is just to save the. Yes. Okay. There. Yeah. But this actually is a topological space because we have a topological space on R. R is a topological space. And so this will actually give us a manifold. And more precisely, this will give us an n times n plus 1 over 2 minus 1 dimensional manifold. And maybe one way to see this is to see that this is isomorphic to positive definite symmetric n by n real matrices. So how would you see that? Well, if you take a matrix here, you would have to send it over here to A times A transpose. That's certainly symmetric. In the exercises, you will see, and if you haven't done this before, it's maybe nice to play around with this, that well, for SO, you will send this to the identity matrix, and it's always a positive definite matrix that comes out this way. And now, since this is symmetric, I mean, if you take all symmetric matrices, that's certainly just a Euclidean space of I guess I have to I did something wrong here. I have to mod out by R plus or something, right? Yeah, or just say determinant 1. Okay, let's do that. Let's do that with determinant 1. That's right. That's exactly what I get here. Determinant 1 matrix. Exactly. Otherwise, I just noticed that I'm off by one dimension. So if you ignore positive definite, then you get a Euclidean space of that dimension. But now getting positive definite is that will give you an open subset of it's going to be an open cone, in fact, and so that will have the same dimension. Okay, now we've already seen, and this is quite important for our story, that xn is contractible. So this is what I write for being contractible. It's a homotopy equivalent to a point is what that means. But maybe I'll just write it out, contractible. And you can have you can consider the action of SLNZ on this space, and this action is properly discontinuous. I don't really want to explain what that means. It just means that, in some sense, it means that orbits are discrete and stabilizers are finite. But importantly, this action is not free. This is not a space that you can just compute homology with, but because the stabilizers are finite, you can actually compute rational homology with it. Let me say it has finite stabilizers, and that's always been thrown around. So let me just give an example. So for example, let's take the identity matrix. So I'm taking the identity matrix as an element in the symmetric space. So this is actually a coset. This times any special orthogonal group. And now, what's the stabilizer of this? Well, it stays in this. I mean, first of all, the stabilizer is, of course, in SLNZ. It's a subgroup of that. But then it also, you multiply a matrix with this matrix. Now you get out the matrix that you multiplied it with, and it stays in the same coset if it's actually in N. I guess N in this case is 2. So this is SL2Z intersected with SO2. Now, what matrices in SL2Z are actually orthogonal? Well, what's in an orthogonal matrix, you have to send a the standard basis to vectors of length 1. What integer vectors have length 1? Yeah, you can only have, well, the standard basis vectors have length 1. So let me maybe if this is R2 and I have Z2 in here, right? Then only these 4 vectors have length 1. So in particular, only finitely many combinations of vectors you can take, and then this is, I think, a group of order 2 or 4 or 4. I think 4. Yeah. 8, maybe 8. Certainly finite is my point. Certainly finite. Okay. I see how it is. And so, yeah. Now the point is that it's finite. And it's very obvious that it's finite, right? And you can do that for any. There are certain matrices that have different stabilizers, but in any case, this implies that I can compute the cohomology of SL and Z with rational coefficients. So I'm just taking, I can put rational also coefficient modules here, but I'm just gonna do with trivial coefficients right now, is isomorphic to the cohomology, the singular cohomology of this space, also with rational coefficients. So that's the main point here, and we've seen that a bunch of times, but I wanted to also state this concretely. And if I have a subgroup of SL and Z that is torsion free, so there's no element that if you multiply it with itself finitely many times is one. For example, I mean, yeah, we've seen some examples, but of elements that do that. But so this is in particular, this is true for all of these congruent subgroups as long as we take a prime bigger than 2.
When we map out xn, we map out on the left, the front of the back.
Yeah, I'm sorry. Yeah, I wrote this here on the right. You're absolutely right. I should write it on the left.
Yeah, so it's
yes. No, you're right. I'm acting by multiplying on the left. I guess you're right about that. It's a defunct of the way that I usually write. Usually all my actions are from the left, but usually also all my quotients I write on the right. So that's a defunct of that kind of notation. But you could just write on the left. I will continue writing it on the right. So be aware.
Just to make sure it's
No, you understood this completely correctly. Very good. So if you have a group that's torsion free, then suddenly this action becomes free. And so we can, in fact, say that for this group, we can take integer coefficients and get the homology like this. All right. So this is all grand, as Graham would say. But now I want to tell you a little bit more about something. In particular, I want to tell you about the Borel-Serre, and I call it a Bordification of xn. So I will focus only on Borel-Serre. There were all these other compactifications. We won't need those for our purposes. Those do serve purposes, a lot of different purposes, but Borel-Serre is the one that we need. Okay, and so what's special about Borel-Serre? Well, just as a reminder, maybe, what do I do? So what happened was so this is the symmetric space, right? And symmetric space is open. It spans in all directions. As we see an example in the second for n equals 2 is the upper half plane. But now in the symmetric space, all of these compactifications that we heard about yesterday, you only attach certain boundary point, you partially compactify it, right? Now, you also have a quotient that's called the locally symmetric space. And now, in the locally symmetric space, if you take the quotient here, now this is supposed to be the one that is compact. This is not compact yet. There's going to be still open stuff. Now, as I said, we're attaching some boundary. Now, attaching some boundary of an open manifold for all of the morphications, this will give you a homotopy equivalence. For all of them this will still be contractible. But the Borel-Serre morphication has the special property that this is also a homotopy equivalence on the quotient, on the locally symmetric space. So in particular, with this replacement, we are still able to compute the homology of the group. And that's very important, okay? So, so this is now a, and we have even more, this is now a compact manifold with boundary. I'm just thinking of it topologically. All the things that I'm going to do with it is as a topological manifold. I don't need the smooth structure. The smooth structure is there. Then it has corners. So sometimes, like you can imagine, you have a two-dimensional manifold. Let's say, I'll make it under the. Let's say this is my two-dimensional manifold, and this is then as a smooth structure. This might have a boundary, but then it has a corner here. Yeah, this is smoothly, it's a singularity, but topologically, I don't really care about the corner. It's still just a one-dimensional boundary, right? That's what's happening here. And I want to give you a concrete picture for n equals 2. And the way that I want to do this is instead of adding on the boundary, I want to go from the boundary, shrink in a little bit, and then cut something off. And then I'll get the same or homotopy, or even a homeomorphic space. So let's say I have this and I embed this in here. This is how I will show how this construction works concretely. This is oh, I forgot the name of the person who came up with. Yes. It's, that's, sorry. What's the second name? Grayson and Stuhler. I remember the name Grayson. Yes, that's the construction they use. So let's do this for the example n equals 2. So in this case, x2 is you can view that as the upper half plane. So upper complex half plane. So this means, in particular, this means all z and c such that the imaginary part of z is bigger than 0. Yeah. So this is topologically, it's an open disk, right? You recall I defined this as SL2 R mod SO2, and I'll let me just explicitly give you this map. This isomorphism, homeomorphism, goes from a matrix like this to AI plus B over CI plus D. Or maybe in other words, if I rationalize the realize, I guess, the denominator, then I get this. This is just a very concrete calculation, as if I multiply this out, the coefficient of I is going to be the determinant of this matrix, so that's just 1, and then I get here AC plus BD over C squared plus D squared. So in particular, you notice that if this matrix is in SO2, that's exactly if AC is in here, sorry, that this is, what is this? This is the scalar product between these two vectors. And this is the length of this vector. That has to be, this has to be 1, this has to be 0. And then there's another a, you also have to say that a squared plus b squared is 0, is 1, but that follows from just being in the, having determinant 1. So this is the same, and so in particular, this is the same as saying that it's being sent, this is being sent to the I, yeah, to the element I. Okay, so this is a well-defined map, and I just wanted to be very concrete, so we can actually play around with these if we wanted to. Okay, so let me draw a picture. So let this be the real line, and I draw it dotted because it's not included in the half plane, right? And now I have the, this is the imaginary line. And so here I have 0, here I have the point I. Now there's some geometry on all of this and everything, but I want to, what I now want to do is I want to tell you what I'm removing. So this is x2, and I'm going to remove something from it to create a boundary. Okay, for that, let me introduce you to so-called horror-balls or Ford circles. So horror-balls. So what is this? Well, for each integer, I'm gonna have a circle of radius, oh, sorry, of diameter 1. So this is, here is 1, there is 2, minus 1, and so forth. So if they are of diameter 1, and then they are touching exactly, and I drew this terribly, but they all touch this vertical line, horizontal line that goes through I, right? And I will view this horizontal line that goes through I actually as a circle that touches at infinity. Like you can imagine, this goes all the way around to infinity, sort of. And now I'm going to add some more circles. Well, I'm just going to add circles so they always touch the real line and each other. So in this case, it's clear this is 1/2, right? Because it's right in the middle. This is 3/2. This is minus 1/2. But I can keep doing that. And now it's maybe a little bit less clear what the circle, where this circle touches. But if I keep doing this, all of these circles always touch at rational numbers. So in particular, this is 1/3, for example. If I do this ad infinitum, then I will, all the touching points are going to be all the rational numbers exactly. And one of the exercises is to show that that this diameter now is 1/4 and this diameter is 1/9, and there's actually a general formula in that vein as a Euclidean metric here, not the hyperbolic metric. Anyway, so these are the horror-balls, yeah. And why do I introduce these? Well, I'm going to shrink these down a little bit, yeah, by an epsilon or by some factor. I'm going to shrink these down, and then I get a new picture. So here's I, I'm shrinking this ball down. Yeah. And now, so this is at 0. This is at 1. Now suddenly they are not touching each other anymore. -1. And in fact, none of these balls are touching each other anymore. I'm shrinking them down in a way that they still touch the real line. Yeah, but not each other anymore. And so now, and then actually I'm going to do the same thing for this ball at infinity. Shrinking that means it's a little bit higher now. It's not at I anymore. It's a little bit higher, right? I'm going to cut out anything that's inside of these balls. So so I'm going to take this area here, and I'm going to say this is going to be my x2, okay? Now, what do I have? I have a space that is actually homeomorphic to the, not homeomorphic, homotopy equivalent to the whole upper half plane, but not all of it. And I got now boundary components. I got an open interval up here. And actually for each rational number, I also get an open interval. Remember that this point on the real line is not actually inside of my space. So really this line is a open interval. Yeah?
Why isn't it homomorphic?
Oh, because I have a boundary now. If this is the boundary here is part of the bodification. Now, as you also see, this is not compact, right? I can go infinitely far in this direction. For example, I can also go infinitely far between these balls. I can just say, oh, I'm going towards a real, an irrational point. And then so this is not compact, but it does have some boundary.
So the reason we did that was touching not going to be right? Is that
Yes, yeah. If it's touching now, it's not connected even, like or it is connected. I don't have space here. It's not a manifold anymore because suddenly here it's only one dimensional. Yeah, that's exactly right. I wanted an area. That's right. But so in particular, I do have to speed up a little bit, or skip something somewhere. But in particular, the boundary of this. Now I get open intervals. This is an open interval. Disjoint open intervals for each element, each rational number, and infinity. Or in other words, this is open intervals are contractible. So these are a bunch of, this is like a discrete set, right? And this discrete set I can also view as actually as maybe lines in Q squared in the two-dimensional vector space. How would I do that? I would send a rational number Q to the span of the vector Q1, and then I send infinity to the span of the vector 1, 0. So that will give me all possible lines inside of Q squared, and gives me a bijection between these two things. Now, in general, the boundary of this Borel-Serre compactification is actually homotopy equivalent to the Tietz building, the nth Tietz building of Q. So what is that? And this is, I should slow down for this as well, because this is important. So if F is a field, then I can make the Tietz building, and this is a simplicial complex. So what's a simplicial complex? A simplicial complex is abstractly, it's a set of points that you have, those are the vertices. So let me tell you what the vertices are. With vertices, non-zero proper subspaces of f to the n, of the vector space f to the n. Yeah. Subspaces. And so you have points, and then I want to put triangles or tetrahedra, simplices between these points, but every set of points can at most have one simplex between them. So in other words, it's abstractly, it's a subset of the power set of these points. So I just take a subsets of the vertex set, and then geometrically I realize each simplex as a triangle, or as each subset that is in there as a subset, as a simplex. What are exactly now? So what are the p simplices? Which subsets of subspaces do I take? A p simplex is exactly a flag. Is a flag. So what's a flag? A flag is just a chain of subspaces. So I take a chain of subvector spaces, for a let's say, what's a two-dimensional simplex? A two-dimensional simplex is a triangle. A triangle has 3 vertices. So I take three subspaces that include into each other. That would be a Tietz building. And if you compare this for Q2, now I have points which are non-zero proper subspaces of Q2 that has to be a line. So I only have lines as my vertices, but then lines can't include each other. So all of the lines are just discrete points. And this is what I saw here, that the boundary is made out of discrete points. Now, the cool thing about this, so this is, it's a simplicial complex, and so I can view this as a topological space. And as a topological space, this turns out to be, this turns out to be a wedge of n-2 spheres. What does that mean? It just means that I take a bunch of n-2 spheres and glue them all together in one point. So maybe as an example, for n equals 3, then this would be S1s. So I glue a lot of S1s together in one point, right? So this is a wedge of S1s. So this is where it comes in to show that something is highly connected. All the homotopy groups, the low homotopy groups, are 0. In particular, this, let me maybe write something else first. But in particular, this means that the reduced homology of this space, let's say with z coefficients, the reduced homology of a wedge of spheres is concentrated only in that degree of these spheres. That's the only reduced homology that this space has. And this is precisely the free abelian group on all of those spheres. So you take these spheres as the generator, as a basis of this homology group, and this is called the Steinberg module. Now this is called Steinberg N of F. And the cool thing about this is that actually, if I take SLNF, it acts on the subspaces, it acts on this Tietz building, so it acts on this homology by functoriality. So SLNF acts on this as a module. That's why it's called a module or a representation, Steinberg representation. Okay, any questions about this? I went a little bit fast and didn't really, I did see some high eyebrows in the, yes.
So like, why do we want to define this modification?
That's your perfect segue to the next theorem. Is there any other question? Otherwise, I'm going to use the segue. The segue leads me directly to Borel-Serre duality. And this states that if I have gamma a finite index subgroup of SL and Z, then I can look at the cohomology of gamma with, let's say, with rational coefficients in high dimensions, let's say close to n choose 2, and that is isomorphic to the homology of gamma in low dimensions with coefficients in, let's say, Q tensor Steinberg of Q. This is where this comes in. This is where, I mean, and it is strongly related to the boundary being this Tietz building, and I'll explain that maybe in a second. We'll see if how far I get with this. But so this, you should view this as a form of Poincare duality. I have some high dimensional cohomology is equal to some low dimensional cohomology. Now be aware that this is a coefficient module. So this actually gamma, so wait, maybe I should say, how does gamma act on this? Well, I said SLNQ acts on this. Now SLNZ is a subgroup of SLNQ, and gamma is a subgroup of SLNZ. So I can act with gamma on this by just restricting to gamma, yeah, to that action. But I should also say that this is a very high dimensional, it's an infinite dimensional representation. Yeah, so this is countably infinite, but still infinite. so this is not, in Poincare duality, you have it with the trivial module, or maybe with the orientation module. I don't know how much algebraic topology you've had, but basically, if you have a manifold, you can relate the top cohomology with the bottom homology and have a similar statement like this. I can be anything. I said that it's going to be close to this, but that was a lie. Just for imagination, it's easier to think about it like that. But really, I can be anything. In particular, I could be negative here. That will give you something that's bigger than n choose 2. But over here, it gives you some negative homology. Negative homology is 0 maybe by convention or something. But it will give you, in particular, that that if you take homology cohomology for k bigger than n choose 2, that this is 0. Yeah, and this is what I said in the beginning, right? A long time ago. Here, I said this is going to be 0 and so we've seen this now. This follows from this Borel-Serre duality. Okay, so let me quickly mention. I'm going a little bit different order than in the notes. Gonna have notes with tech. I don't know if they're there yet in the resources, but we're gonna supply those to you. So I can make sure I can stop on time. But so one of the main points of this talk is the following conjecture. It's called the Church-Farb Putman conjecture. And it says that if I take the codimension I cohomology of SLNZ with rational coefficients, or in other words, using Borel-Serre duality, the ith homology with coefficients in Q times Steinberg, that this is 0 for I smaller equal to n choose 2. N minus 2. Maybe I want to write this as n is greater equal to I plus 2. That's the same thing, right? So for large n, the conjecture says codimension I vanishes. That's the conjecture, and so Jenny is going to talk about this conjecture for I equals 0, and then later I'm going to talk about it for I equals 1, and then maybe in the future directions or in further directions in the last lecture we're going to talk about this a little bit more generally. What I have now left to say is maybe an idea of where this Borel-Serre duality comes from. Saying something about Poincaré duality and using this Borel-Serre compactification, namely that this is a compact manifold with boundary. But I think if I want to stop at 12:30, maybe you will have to read about that in the notes. Is that preferable, or would you rather hear about it? Yeah, let's have questions rather than go into something new and that's technical. Yeah.
So if instead of looking at SLN R, we take a locality instead of R, we still get not a symmetric space, but we get a building. And
yes, very good question. Very good question.
So do we have also,
yes.
Duality,
yes.
But equality with the cohomology of the matrix.
Very, very good question. So let me tell you, that's maybe a very good, a grand time to how to spend the last minutes. If you, instead of Z, took any other number ring, so any other ring of integers in a number field, you would still get this Borel-Serre duality. Mind that the n choose 2 is going to be a different number. That's going to depend on the dimension of the. This is actually the dimension of the symmetric space minus the Q ring, this number. And you will have the Steinberg module of the number field. Now, I just want to point out again, this actually is a free abelian group. Maybe I haven't pointed that out. It's an abelian group, but it's actually a free abelian group, despite being infinite dimensional. And now this is then an infinite dimensional Q vector space. But so you have this for SLN of all number rings. Even more so, you can take any reductive, let's stick to semi-simple algebraic group. I think it's true even for reductive. And you can also have to watch out here for the dimension, and you have to have a different so-called dualizing module here, but it's also going to be something related to Steinberg. There is as you said, maybe for this symplectic group, there is also a building corresponding to the symplectic group made out of isotropic subspaces. Yeah. And then you will also have such a Borel-Serre duality for those groups.
What I was asking as well is, not if we jump group, but if instead of looking at the symmetric space,
yeah,
we look at the duality splitting
yeah.
of a PATZT.
You want to do SL groups.
I think that, yeah, that's also true, right? I don't know enough about S as arithmetic groups, but I do remember that the paper of Borel-Serre explicitly says on the top homology for S arithmetic groups. So maybe Aurel, do you know if Borel-Serre is also true for that? You don't know. But I think I think maybe Philippe knows. Yeah, I think it's true, because especially since the paper is called cohomology of S arithmetic groups. So I believe that's true. Anyway, my time is up. Thank you for your attention. I'll stop here.